Thank you very much, Lars. I'm pleased to be here. I wish I was there in person, but perhaps next time. So I'm going to be talking about high performance computing. And just to give an outline here, we're going to look at some of the issues that high performance computing has and big data, which is something which, of course, is used in high performance computing. And we'll take a look at some of the killer apps for high performance computing, big data, and maybe the elephant in the room, machine learning. So first, I just want to point out some of the see, I'm having a problem here with my, there it is. I want to point out that, for years, science has been done through a number of mechanisms. So science has been done through theory. Think of it as a paper and pencil design. We've done science through carrying out experiments, building things and using them. And those two things have limitations. Sometimes it's too difficult, too expensive, to actually build an experiment. Think about an experiment where we have two galaxies colliding. That's an experiment that we would like to carry out, but we can't carry out that experiment in reality. We can't physically move two galaxies together and see what happens. We'd like to understand what happens when perhaps birds get ingested into the engine intake of a jet in flight. Now that's an experiment that, well, actually it has happened, but we would like to model that to understand better how we can prevent or to modify the results of that. Or think about climate modeling, where we would like to understand what happens in the long-term effects. Those are experiments that we really can't do. So we turn to simulation to carry out these experiments. So simulation has become, let's call it, a third pillar of science, augmenting theory and experimentation to help us in understanding the world around us and to push the frontiers of science back. So computational science, which is at the heart of simulation, is used to do these things. Computational science uses high performance computers to effectively simulate these phenomena. And high performance computing takes the many forms, but a basic high performance computer or a supercomputer starts out with based on a common chip. So we think about a common chip, which today has many cores or many processors in it. In this cartoon here, we have 8 cores which are connected some way on this chip. These cores can share information, passing information from one chip to another chip, usually through memory. They share a common pool of memory. And we think about taking those chips and putting them on a substrate or on a board. So we think about a board or a node which contains multiple chips, and each of those chips has multiple cores. And again, we can pass information around in those chips. Today, we think about augmenting that chip with an accelerator or a GPU, a graphics processing unit. The GPU is there to provide additional computational support. It's an accelerator. It can do floating point computations much faster than that chip can, than those cores can. So the strategy that's used is to get a chip, put a GPU next to it, and then offload computations from that socket over to the GPU, have the GPU perform that operation, and then the data comes back to the chip and processing continues. So in some sense, you have two things going on. You have computations going on within the chip and computations going on within the GPU. And it's the programmer's responsibility to coordinate those two. And we have, on a node board, we have multiple chips, multiple sockets with with GPUs, maybe multiple GPUs connected to each of those sockets. And that's considered a node in the supercomputer. And then information can flow within that ensemble, passing things from core to core, from GPU to GPU. And of course, we're not satisfied with that. What we're going to do is to take that node board and put it into a cabinet. So now we have a cabinet or a rack, which we fill up with these node boards, each composed of multiple chips with GPUs attached to those chips. And on those chips are multiple cores. And information flows around that system, perhaps from chip to chip, between within a node, internode, and then also across those nodes through the cabinet. And the programming model for doing that may be a shared memory programming model, or it may be a distributed programming model where the programmer explicitly has to pass messages containing information between various processes in a program. And of course, we're not going to be satisfied with that cabinet. What we do is to take multiple cabinets and fill up a room. So a typical computer, supercomputer, has multiple cabinets connected through an interconnect network composed of these node boards, each node board composed of chips, multiple chips, each of those multiple chips attached to a GPU. That's sort of a common mechanism for building a supercomputer. And again, we fill up a room. So a room, think of, in the case of one of the largest supercomputers, think of a room about the size of 2 tennis courts. And that's filled up with these cabinets, which are coordinating a computation, a single computation, with millions, literally millions of cores, processors, that are coordinated by the programmer to solve a very challenging problem. So that's a typical supercomputer. So we've been looking at supercomputers for a long time. My colleagues, Hans Moyer, Horst Simon, and Eric Strohmeyer and myself have put together this list of the top 500. So this is a list of the top 500 supercomputers in the world. And that list comes out twice a year. It comes out in November and in June. And it's used to gauge the market for supercomputing. So what we do is we have a benchmark that we run on a computer, and we look at the performance of that benchmark for a given problem that we're going to solve. And the problem that's solved in this benchmark is a very simple one. It's a linear algebra problem. It's a problem where we have a matrix A, we have a vector B, and we'd like to compute a solution X. So AX equals B as the linear system of equations. The matrix A is dense. It's filled up with numbers, 64-bit floating point numbers. And we're looking for a solution. So we pose that problem. We give an algorithm that must be used, Gaussian elimination with partial pivoting. It's the way we learn how to solve that problem in high school. And we do an implementation optimized for a given computer. And then we look at the rate of execution for solving that problem. So the number of operations that's performed for solving that problem can be made pretty precise. It's 2/3 n cubed floating point operations, where n is the size of the matrix A. So if you have a matrix of size 100, it's 2/3 100 cubed floating point operations that will be performed. And then we look at the time it takes to solve that problem using Gaussian elimination with partial pivoting. Now you can make n as large as you want, make n as big or as large that'll fill up your computer. That's when you get the best performance. This little graph is intending to show that as you increase the size of the problem along the x-axis, the performance will increase until you reach some asymptotic point. And you want to run your benchmark at that asymptotic point to capture the best performance. Again, this list is updated twice a year, and you can find all the results there at that website, top500.org. So today, the state of supercomputing looks something like this. This is based on, although this slide says 2019, it should say 2021. All the computers on our list are over a petaflop, over 10 to the 15 floating point operations per second. So a floating point operation is an add or a multiply of 64-bit operands. So all the computers, all of the 500 computers are at that point or greater. So 10 to the 15 operations a second. What we see is there are 3 architectures for building these supercomputers. One of the architectures is just use commodity processors. Just go out and buy a bunch of Intel processors, put them together in a box, connect them with a high-speed interconnect, maybe InfiniBand, and we're going to call that a supercomputer. And we have models of that on the top 500 list. The second one is using commodity processors plus an accelerator, a GPU. I mentioned that earlier. And we have 145 of the 500 computers use that model of computation, with NVIDIA being the largest GPU that's used. And the third model is to use very lightweight cores. Lightweight in the sense that they don't have all the sophistication of an Intel processor. They're much simpler, but we're going to use lots of them. And IBM had a machine called the Blue Gene. In China, there's a machine called the Tahu Light, which they have a specially designed processor, which was put together specifically for supercomputing. Both the Blue Gene and the Tahu Light are based specifically for the supercomputing market. So those are the 3 architectures that we see. China turns out to be the top consumer of supercomputers and also the top producer of supercomputers. So they manufacture the most supercomputers, and they also are the ones who buy the most supercomputers. And that's a very striking change. In China, back in 2001, there were 0 supercomputers in China. And today they're the top producer and consumer of supercomputing. It's interesting. There's a lot of interest in supercomputing worldwide. It's growing. And if you take a look at the list of the 500 fastest computers, what we see is half of those computers are used in industry. So not in science, not in research, but in industry. So industry gets it, that these supercomputers can help with their industry, give them a strategic advantage, some competitive advantage in the market, and they're willing to invest in these high-performance computers. Intel processors have the largest share of those supercomputers. 86% of the 500 supercomputers are based on Intel processors, and AMD has 10% of the supercomputers. And I want to go to the next slide, but it's not producing it. There we go. Okay, so this is a graph that charts the top 500 list from when we started back in 1993 until today. So what we're looking at here, the red line is charting the computer that's at position number 1. So that's the fastest supercomputer. And we see that it's over 400 petaflops is the fastest supercomputer today. And the guy at the bottom of the list is at 1.5 petaflops. And that's this orange line at the bottom is the guy just at the bottom of the list. So that brackets, the red and the orange bracket, the 500 computers. The blue line that you see there is the sum of the 500 computers. So that's an artificial number, the sum. You just have an Excel sheet which adds up the 500 computers, and there you get a number which is in the exaflop range. But you could see where supercomputing has been. So back when we started this list, the fastest supercomputer was about 550 gigaflops worth of computing power. Now the laptop I'm using to give this talk, in some sense, is an Apple laptop. It has a few processors in it, and I can run the benchmark on it. And when I run the benchmark on my laptop, I get something in excess of 100 gigaflops, so 100 billion floating point operations per second. That's the rate of execution. Again, we're talking about operations of adds and multiplies of 64-bit operands. So that computer is, my laptop is, a machine I use every day. I mainly use it for reading email, if I want to be honest about it. And that's an incredibly powerful system. And not too long ago, if we take a look at my laptop and compare it to supercomputing, we see that it was actually faster than the first supercomputer that appeared. And that first supercomputer back in 1993 was a Thinking Machines CM5 with 1,000 processors that was used at Los Alamos National Lab, and that was used to carry out nuclear weapon design. So I have a laptop here which is incredibly powerful when measured against the supercomputer of the day in 1993, used to carry out some of the most sophisticated computations that were done in that period of time. So incredible changes in a short period of time. This is a historic graph. We notice a few things in this graph. There seems to be a few discontinuities that occur. And there's a discontinuity that occurred around 2007, at the bottom of the list here around 2007, and another one that appeared roughly around 2013. And if we take a look at that, we see that we can interpret that partially because of things like Moore's law declining. It's not ended, it's just slowed down. And Dennard scaling ending. So Dennard scaling was a powerful electronics ability where we could enhance computer chips, making them smaller, using essentially less power and having them much more powerful. But Dennard scaling ended because of the miniaturization caused too much heat to be generated, and we couldn't continue to enhance the cycle time of our chips. So we had to freeze or stop enhancing the cycle time. And that's why today we don't see cycle times getting much larger than 3 gigahertz for our processors. This is a historic list of performance. What we're seeing here is a list which charts things, looking at the how things have progressed. We see that we have somewhere in 2097 the first teraflop computer. That was a machine called the ASCII Red at Sandia National Laboratories. About 11 years later, we had the first petaflop computer, so 3 orders of magnitude enhancement, 10 to the 15 operations per second at Los Alamos National Lab in a computer called Roadrunner. And today we're anticipating exascale computing sometime later this year. So China and the US are in, let's call it a race to get to exascale. China is saying that they'll be there in 2021, although there are rumors that they actually have a machine today. The US is projected to reach that sometime later this year, a computer that will achieve 10 to the 18 floating point operations per second for use in scientific research. This is a list of the 500 computers that we have today. And think of this as each of these rectangles that you see represents a supercomputer. The area of a rectangle represents the performance that it achieved. So the fastest computer is a computer in Japan. It's the Fugaku machine. So that's the largest green box that you see there, followed by a box in the US. So the US has the second largest system and the third largest system, and then China has the next one. So if you take a look at the number of rectangles, China has the most with 186 rectangles. The US has 123, and you can go on down the list and see the number of supercomputers in the list. But China leads that list. In terms of producers of supercomputers, we're looking over time from 1993 until today. And here we're charting out who produces the supercomputers. And you can see that the US was the major manufacturer of those machines until around 2009. And then other countries became more in the producing. And China today has really dominated the market in terms of high performance computing. Most of the machines that are on the list from China are at the bottom of the list, not at the top of the list. That's an important point to make, but they still dominate the list overall. Again, all of this data is contained in the website top500.org. Okay, this is the number 2 machine. I want to illustrate it. It's a machine that I use frequently. It's here at Oak Ridge National Lab where I work. It's called Summit. It's a machine which has a peak performance of 200 petaflops. It's composed of a node which has 2 IBM Power 9 processors. Each of those have 22 cores. And also there are 6 NVIDIA GPUs on this node. So 2 sockets for IBM, 6 GPUs attached to a node that can do computations. And then there are 4,600 nodes in the overall system. So it's a big machine, takes about 2 tennis courts, has incredible amounts of memory associated with it, very fast bandwidth. There's a few interesting facets to this machine. Well, I said the peak performance was 200 petaflops. That's for 64-bit operations. If you do 16-bit operations, which can be done on this computer, 16-bit floating point, we exceed 3 exaflops for the peak performance. The other thing to note is that most of the power from this computer comes from the GPU. So most of the floating point power comes from the GPU. 97% of the performance is coming from the GPU. So in order to use this machine effectively, your program, your application must benefit from those GPUs, or you have to program it to use those GPUs. And again, I've mentioned that there's this trade-off or bouncing back and forth between the CPU and the GPU. The programmer has to manage that. There's no automatic stuff here. So the programmer has to write something which passes data to the GPU and then passes data back to the processor and then communicate. So in this machine, there are 27,000 GPUs. Today, the street value for those GPUs is about $10,000. So it's an incredibly expensive machine. Now, this machine was not bought based on that street value, but these machines are not inexpensive to build. So I mentioned one benchmark, this benchmark called HPL that does a linear system of equations based on a dense benchmark. Most of the machines that we have on that list achieve very high rates of execution based on that benchmark. But that benchmark is not really relevant to the applications that we have today. Applications that we have today, these machines are usually used to solve large-scale 3-dimensional partial differential equations that arise in the simulation that's trying to be performed. And those 3-dimensional partial differential equations generate a system of linear equations, but that linear equation is not dense, it's sparse. So it has a sparsity pattern. And the algorithm that's used to solve that problem is different than the algorithm that's used to solve the dense problem. Here we're going to be using an iterative method that's used to get an approximate solution and then carry out some iterations to improve the accuracy of that solution so we get down to something which is 64-bit accurate. So the matrix has a different representation. It's not based on dense computations. It's based on sparse computations. And the character of the algorithm is quite different. The first algorithm, based on dense calculations, it's basically carrying out a matrix multiply of dense matrices. This algorithm used in HPCG, this other benchmark, is based on passing data around. So data movement is much more critical in this application than it is with the other benchmark. So this benchmark is highlighting the fact that the architecture is doing data movement and trying to understand better what the cost is of that data movement. So this is a table of the top 10 machines in the case of the HPCG benchmark. And the winner is this machine from Japan, Recipient. It's a very powerful machine with large numbers of cores in it. For solving a dense problem, it achieves a very high rates of execution, 440 petaflops. And for this benchmark, it achieves 16 petaflops. So it's achieving only something on the order of 3% of the theoretical peak. And I just point this out that most problems that are solved on high performance systems really achieve a small percent of the theoretical peak performance of those machines. And you can go down this list here and see the relative poor performance relative to the theoretical peak performance for these machines. It's just another way of measuring things, perhaps more relevant to the computations that are going on today on these computers. So we have two benchmarks, HPL, this dense problem, and the sparse problem, and they present these what I call bookends. So the black line here is the theoretical peak performance for a bunch of machines on the top 500. The x-axis is the number one machine up to some number of machines. And the green line is the LINPACK benchmark, HPL, very close to the theoretical peak. And the blue line represents this HPCG benchmark, a different benchmark measuring different characteristics of the hardware, more relevant to the kind of computations that are done today, showing that it's far below the theoretical peak and much more with what people see. Today, there's a lot of interest in exascale computing. The US is making a big investment in it. We hope to get to exascale sometime later this year or early next year. The machines are very expensive. So the machines that are being thought for exascale cost around 600 million US dollars for one computer. And in the US, they're putting together 3 of these exascale machines. So the price tag is about $1.8 billion for the hardware. That's 3 computers, $1.8 billion. And that doesn't include the software or the algorithms or the people involved with it. That's just the hardware cost. So you see, it's a very large investment. China has also an investment in high performance computing, which is similar to the US in terms of its plans. They're being a little bit more mysterious about when they're going to announce their computer. There are rumors that it exists today, and going forward, we'll have to see. In the EU, there's also plans for building high-performance machines. It's pushed out a little bit further than US and China, but there are plans there to build it. And Japan also has plans to build their machines. Japan today is number 1 in terms of the high-performance computing. They have the fastest computer, and that computer is estimated to cost $1 billion US dollars. So again, it's a very expensive computer being used to solve some of the most sophisticated problems. You have to think of these computers like the sophisticated scientific instruments that we have. Think of it like a Hubble telescope. Hubble telescope is very expensive to put up there and to maintain, but it provides an incredible wealth of scientific information, and we're willing to make that investment. The same thing is true with these supercomputers. It's an instrument that's used by scientists to push back the frontiers of science, and that's what they're being used for. Again, I mentioned this investment in high-performance computing, $1.8 billion in the US, and that's going to go for these 3 computers. One is going to be at Oak Ridge National Lab, perhaps the first exascale machine. A second one is going to Argonne National Lab just outside of Chicago, and a third computer is going to Lawrence Livermore National Lab in California. So that's the setting for exascale in the US, and that'll unfold over the next year or 2. China also has plans for exascale, but because of some embargoes that the US has placed on US technology, China has made a statement that they're going to build their own technology, anything but from the US. And they have 3 machines that are being designed. They have a machine that's going to be based on a Chinese processor from a company called Shenwei. The current machine is in Wuxi, China, just outside of Shanghai, and it's a machine that will be used for scientific computing. Another one is a machine from the National University for Defense Technology. Today, the machine that came from there is the Tianhe 2A, and they're building a machine called the Tianhe 3, which will be based on a Chinese ARM processor and an accelerator that's built in China. And the third one is from Sugan, a Chinese company, an integrator who has access to the x86 architecture that they're able to manufacture and build on their own. Again, I mentioned this embargo that was placed on Chinese U.S. technology, and that's limiting some of the things that can flow into China. This is a historic graph looking at what's happened to the technology of computing over time. Moore's law is driving the number of transistors, and we see that going up. We have this issue with cycle time increasing with our processors and cores, number of cores. Because of the transistor count, those transistors are going into cores on a chip, and that has also gone up. But we're reaching some limitations with the slowdown of Moore's law, with the inevitable break of Dongarra scaling. We see power being capped at around a certain point. Again, that impacts the cycle time. The cycle time impacts the power requirements of these systems. And because of Moore's law slowing down, the number of transistors will decrease, and that will limit the number of cores on these processors. So what happens after this is the question. With these slowdowns, what's the impact of this? And we see a number of things happening, potentially happening in the future in terms of architectures. One thing is we have this notion of advanced architectures based on certain things that can be exploited. Dark silicon, turning off certain components of our silicon when they're not needed, and other facets of the architecture. We also see different models being exploited here in terms of how those chips are put together. And we have different mechanisms for utilizing things, perhaps going to quantum neuromorphic computing in the long term, although those things are not certainly present currently or on even the near horizon for our high-performance computers. So there are things that will mitigate these slowdowns in Moore's law and the end of Dongarra scaling, and we hope that they can take us forward in terms of computer architectures in the future. And I'm running out of time here. Let me just mention a few things. Machine learning is an important aspect of high-performance computing. It's a tool that computational scientists are using today. It's being used in climate science, and there's a whole collection of areas in genomics it's being used. We see it used in drug discovery, and deep learning is being deployed there. We see it being used in disease prediction. It just is an incredible way to help predict the disease being used in COVID and monitoring and looking at how drugs can be used for that. So it really is providing us with a fantastic tool to help science overall. And hardware manufacturers understand that and are targeting future machines in that way. So let me just conclude here saying that the HPC hardware is constantly changing. Early on, we had scalar machines, and they changed to vector, and then we had distributed memory machines, and then we had accelerators, and today we have mixed precision that's being used in our scientific computing. We have these revolutions that are taking place in high-performance computing, deep learning, edge and AI-based computing. The algorithms and software have to keep pace with the hardware changes. Hardware is running very quick, and the algorithms and software always play second to the advances in hardware. Basically, hardware gets thrown over the fence, and the algorithms and software people have to catch up with that. But I have to say that there's plenty of room at the top. That is, we see a lot of margin between the peak performance of computers and the achieved performance. And by software and algorithm advances, we can match that, we hope. So in a rift on Richard Feynman's, there's plenty of room at the bottom. There was a paper written that appeared in Science recently. There's plenty of room at the top. for modifying things and for enhancing the performance of our applications on today's high performance computers.